Hello everybody and welcome to the NPTI online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 34 where we will continue to understand the mobility effects in a MOSFET and some reliability issues, for example self-heating effect and NBTI. So, these 3 or 4 topics we will be dealing in next lecture. So, we had already finished phonon and lattice. Let me come to the Coulombic scattering. Coulombic scattering is possibly the most easy to understand. It is almost like an electrostatic scattering which is happening between two charged particles. One is basically energetic, which is the charge carrier which is moving, and another is the stationary, which is the target there. Now, this scattering is not a physical scattering, but it is more of a action at a distance sort of a scattering, right, where you basically have the charge carriers coming and then hitting the target. The target has got electric field nearby it, within which influence if the projectile comes, it will bend its path, as you can see on the right hand side the figure here. The distance between the projectile, right, this projectile and the center of the target is defined as the impact parameter, right. This is known as the impact parameter. So, impact parameter is defined as the distance between the projectile and the target. So, if there would not have any collision, this distance would be also defined as the impact parameter had there been no collision. Now, because there is a collision, they start moving in this direction and there is a scattering angle attached to it, which is defined as the theta in this case. Higher the obviously the charge, lower the velocity, more will be the scattering angle. Now, we are assuming that these are purely elastic collisions which are happening here, which means the energy and momentums are always sort of maintained in this case, or there is no violation here. The Coulomb force therefore will be given as 1 by 4 pi epsilon naught into Z1 Z2 is basically the charge. This is the charge of the electron, this is the charge of the target species, and divided by r square. So, q into z is the total charge Z1, q into Z2 is the charge of the target. So, this is for the target, let us suppose, and this is for the electron or the projectile, and you get the force. So, as you can see, higher the charge, more will be the force. So, this r is basically the distance between the two, and that lower the value, higher the force. So, this r value is the distance, it is the physical distance between the projectile and the target. So, you see, as the projectile starts moving towards the target, the force actually increases in a parabolic fashion. If you reduce r from r to r by 2, then basically the initial value was r by 4, this will be r square by 4. So, the force will increase by a factor of 4 times, right. So, which means that if the distance reduces by half, the force actually increases by a factor of 4 times, right. That is sort of a substantial increase in terms of force applied, and this is one of the reasons why you get a Coulombic scattering. Let us look at from the point of view of MOS device. The MOS device, the target is basically a charged boron or a charged arsenic atom, and this is the projectile. With n type it is electron, for p type it is a hole. So, surface roughness scattering, understood phonon scattering, and we understood Coulomb scattering. How do you actually take into consideration all of these scattering phenomena together, and that is done by what is known as a Mathiessen's rules, right. And this is an approximate method for combining mobilities to calculate the total mobility in a material under the influence of an electric field. Okay. So, now you see we define the probability that a carrier will be scattered by a mechanism I can be either of the 3 within a time period dt is given by dt by tau I. So, tau I is the mean time between scattering event due to this mechanism. Now, the probability that the carrier will be scattered by any mechanism within the time t, therefore, if you add those two together, summation of I dt di, where tau I is the mean time between scattering event due to mechanism phonon, Coulomb or surface roughness, right. Now, if you look very carefully here, then it is effectively this converts to 1 by mu phonon, this converts into 1 by mu Coulomb, and this converts into 1 by mu surface. So, you do almost like a resistive in parallel addition, right. resistance and parallel addition. So, total mobility will be 1 by mobility of phonon plus 1 by mobility of Coulomb plus 1 by mobility of surface roughness. So, that is how you define this particular mechanism. Now, you see how did I reach to that conclusion is even intuitively we will reach to the conclusion that if the mobility is basically large, if the mobility is large, it can only happen when the mean time between scattering events is relatively large, right, and therefore 1 by tau I is proportional to 1 by mu, and that is the reason this can be mapped to each value. Higher the value of tau I, more can be the mobility, because you give more amount of time before each scattering event to occur, larger value of mobility, and that is the reason this phenomena of mapping, right, this phenomena of mapping seems justified. This is the Mathiessen's rules which we apply. So, the Mathiessen's rules tells me that the overall mobility will be always less than the least, right. That is a rule of thumb when you apply a mobility model. Let us now come to some reliability issues in a MOSFET before we close this week's lecture series, and we will do here some degradation models and high electric field model. We will look into what is known as a hot carrier effect, we will look into NBTI, and then we will look into the self heating phenomena, because at least out of these three, two will be used for the subsequent lectures when we do the reliability of double gate, FinFET, Fox sheets and so on and so forth. So, understanding the basic fundamental without going into too much detail is what we are going to do, at least for this part of the lecture. Now, let me come to the first of all to the hot carrier effects. Now, we are all aware of the fact that as you reduce the dimensions of the device, you typically have a high and high electric fields, because even if you do scaling of VDD and L, so the longitudinal electric field Ex will be given as VDD divided by L. So, even if you scale down your VDD and L, even if you scale down your VDD and L, your still electric field in X direction, assuming this to be as X, will go on increasing. Similarly, if you scale down your Tox, your Y direction electric field oxide thickness, if you scale down, will increase, right, which means that the net electric field will go on increasing as you go from a higher technology node to a lower technology node. This causes a degradation of the device characteristics, right. So, there is a heavy degradation of the device characteristics when you apply an external electric field, and the external electric field is actually increasing with passing technology node. There are two phenomena which comes into picture. One is the hot carrier effect and the other is NBTI, which is negative bias temperature instability. This is the basic diagram of a MOSFET, and as you can see here, I will explain to you maybe in the next slide to show it to you. Just keep this in mind, we will return back to this slide later on. Let me come to the hot carrier effect. Let us suppose the electron is moving, high electric field is generated, the electron gains energy. While doing so, let us suppose it enters into any space charge region and generates large number of electron hole pairs by impact ionization. What is impact ionization? A very high velocity is coming, it strikes one of the charged particles, energy is given to the lattice, energy is more than the band gap of silicon, there is a sudden generation of an electron and hole pair, right. However, please understand, in the depletion region of the MOS devices, there is a strong electric field present. So, what will happen is, so even before the recombination of electron hole pairs, they will tend to segregate very easily, and that is what is written in the second part, that as the electric field in the drain junction space charge region increases, electron hole pairs can be generated by the impact ionization and they can be easily separated or swept to the drain. So, if you look at the right hand side, you see the electrons, because you have a positive bias here, the electrons are moving towards the drain and the holes which is given by cross are moving towards the surface. This is known as a drain to bulk current, right. There will be a drain to bulk current which will be there. This is the edge of the depletion, this dotted curve is the edge of the depletion, this is gate and I have the oxide layer here, this is my silicon, within the silicon this is my depletion edge which you see here, this is my depletion edge, and I have these positive charges actually being thrown towards the substrate and the negative charge is being attracted towards the drain side and resulting in a excess current which will be there. Now, some of the electrons can also be dragged through the oxide layer into the gate, right, because there is a positive gate voltage in case of an n channel enhancement mode MOSFET, and that will result in a direct sort of a tunneling through the oxide layer into the gate region, right, and this is induced by the positive gate voltage which you apply. This phenomena is defined as the hot carrier effect phenomena. Now, since these generated electrons, as you can see here, the negative charge is moving towards the drain, and the positive charges are moving towards the substrate, right. However, there are few which are moving across the oxide layer into the gate region, right. So, these generated electrons have much larger energy as compared to a thermal equilibrium value. Now, if the electrons have energies of the order of 1.5 electron volt, they may be able to tunnel through the oxide layer directly into the gate region, provided my oxide thickness is also very small. However, there is one more case which a sort of a second order, third order phenomena, that there are large number of traps also available within the oxide layer, right, and these traps are basically, as the name suggests, they are traps. So, they are basically low energy sites where electrons moving from the depletion region through the oxide can easily sit inside these traps, right, and they can produce a net negative charge density in the oxide. When they produce a net negative charge, it produces a mirror positive charge onto the silicon interface, and therefore, you require to have a larger gate voltage to invert the channel, and therefore, the threshold voltage rises. And these are the few problem areas which devices face. There are many techniques now available by which you can actually reduce these negative impact of hot carrier effect onto the device. Just for information's sake, the probability of electron trapping is usually less than that of hole trapping, and electron the energetic electrons as they cross the silicon dioxide interface can generate additional interface trap charges, right. So, there are three phenomena which is occurring here, that there will be a current flowing through the drain, there will be a current flowing through the substrate because of the EHP generation, there will be also a current flowing directly to the gate side because of direct tunneling. Also, it will produce large number of interface states at the silicon dioxide interface for these free electrons. Now, the probable cause of interface generation obviously is because of the breaking of the silicon hydride bonds. Why? Because when you actually oxidize the silicon, you will have silicon dioxide, but you will also have some of silicon hydrogen bonds available, and when they break down, they will leave a dangling silicon bond is present, and they form the interface states. So, basically dangling bonds are available which will be low energy states where the electrons can sit there, and this. So, as I discussed with you, this will cause a change in the shift in the threshold voltage. That is what is written in the second statement which I have already discussed with you, that there will be a shift in the threshold voltage. Additional, there will be surface scattering, and there will be further reduction in the mobility which will occur. And the hot carrier charging effect is a continuous process. So, the device degrades over a period of time. So, it is basically degradation goes on for a large amount of time. One methodology by which people have actually there are techniques which are available. One is the channel engineering, and one is the LDD structure, which is known as a lightly doped drain structure. When you make a lightly doped drain, means your doping concentration is relatively small, your depletion widths are therefore relatively large, which makes the electric field small. When the electric field is small, the probability of impact ionization and hot carrier effects are reduced, right. So, this is one of the techniques by which you can actually reduce the formation of electron hole pairs to a larger extent, right. So, this technique is basically known as the channel engineering technique, and it is to do with that you dope it with very lightly doped drain, let the depletion thickness go high and high. As you make the higher and high, the electric field reduces, and therefore, you have less impact of impact ionization and hot carrier effect. The next one is obviously a very straightforward technique, is lower the supply voltage. However, this might not work on a longer run, because just lowering the supply voltage has got many other problems available to us. and especially the latency. But if you lower the supply voltage, again the idea is reduce the electric field. If you are able to reduce the electric field, you can do many other things with that, but that then this is not a very I should say a gallant way of, or a good way of doing solution of the job. The better solution is the first one, the LDD, and the other two which are presented now, the material engineering which we do. So, another way of material engineering is that let us provide a material which will reduce the hot carrier effect, right. And what we will try to do is that if we have a thermal property of the material is such that it will reduce the hot carrier effect. Say for example, silicon germanium can be used in this case. That is a very good idea about material engineering. Another good way, and this is where we will be delving more and more as we move ahead in the lecture series, is device scaling. So, when you actually do something known as, if you are interested you can work it out, something known as Dennard scaling theory. If you go ahead and look at this Dennard scaling theory, you will see that you lower the channel dimensions, but you lower the VDD, the power supply as well. Once you do that, you end up having a better scaling. The second thing is, if you are able to make the control over the gate much higher, then these effects becomes lower, which means that if gate has a better control over the channel, then these phenomena will be applicably reduced or very much reduced. And one of the examples which people follow is basically your FinFETs and GAA devices. FinFETs and gate all around devices can manage the effect. Let me come to NBTI, or negative bias temperature instability effect. Now, if you apply a negative bias on the gate side of a MOS capacitor at relatively higher temperature, then this can cause a large buildup of positive charges in the oxide, sort of a mirror charges, because you applied a negative charge and you have a metal in the middle, you will have a positive charge in the oxide. When there is a positive charge in the oxide, density of states will increase in the oxide layer. Therefore, to turn on a p channel MOSFET, the gate electron is negatively biased with respect to N body, but then your threshold voltage will change, right, and the device temperature can go as much as 100 degrees centigrade. HCI is basically your hot carrier injection, and NBTI is the region, this is the NBTI region which you see. This is also NBTI which you get, this place, where you have large elevated temperature and build up of large number of positive states. So, these positive states which I have shown by the crosses here, these positive states in the oxide layer will grow a negative state, and your threshold voltage has to change in order to switch on the device. This is basically a negative bias temperature instability, and these are unstable at very high temperature. Now, as you can see, as has been pointed out, that and as you can see that for a p channel device, therefore, since this is a cumulative effect, as the time goes on increasing, what happens is that the threshold voltage will change, will shift. So, this is a cumulative, NBTI is a cumulative phenomena. That means you do now and then you do it again once more, they go on adding up. This because the surface states goes on adding up, and therefore, you require a larger and larger potential in order to switch on the device, and therefore, the threshold voltage changes. The device degradation due to NBTI is always a function of the process of the insulator growth, because if your process of gate insulator is very nice without any surface states, then you are better off, right. And therefore, NBTI becomes more worse, obviously a function of temperature and the electric field across the oxide. However, device degradation is almost insensitive to channel length. So, even if you have short channel length or large channel length, NBTI does not affect it to a larger extent. Now, so therefore, to sum up NBTI and HBI, these two, hot hole effect and NBTI, hot carrier effect and NBTI, is a combination of both of them, right, and that makes it to be the device to work in a bad fashion, or that there is a general degradation of the device and it is a reliability issue of the device. Let me get to the last part of the talk, and let us give you an idea about what is known as self-heating effect. What happens is, as the transistor switches on, you have a on current flowing. Now, if I say that ion square, right, ion square into R, where R is the resistance offered by the channel to the device, if ion goes on increasing, ion square into R goes on increasing, and as a result the heating is also increasing. So, if the heat does not get appropriate ways to dissipate across the device, the heat will go on increasing, right, and the heat structure will go on increasing, there will be increase in the temperature. So, a general rule of thumb is that if there is a 10 to 20 degree increase in the temperature, the device lifetimes are reduced by a factor of 2 times, right. And this is the major concern, and this is what is known as a self-heating effect. Why? Because the temperature rises, many problem comes into the reliability of the device. This is known as hot carrier effect in this case. Say for example, look at this picture, this is an N channel CMOS transistor, and I have an oxide layer here. I have a source, gate and a drain, right, and I have this oxide layer, I have the box layer here. This is a buried oxide, right, this is a buried oxide, which is a large substrate oxide of the order of thousands of angstrom here, which is being drawn here. So, any heating effect which is happening in this region, the active region of the channel, does not get a path to move across except this and this, but this side is all blocked up, and similarly oxide is also blocked up. They are bad insulators of heat, and they will not let the heat to dissipate outside the device. That is the reason the temperature goes on building up, and moreover as the temperature shoots up, it helps the device to generate more current, right, because of EHP generation or otherwise, and that adds value to the problem or adds more and more problem to this device. And as you can see, the refers to the phenomena where the device temperature increases due to power dissipation within the device itself, nothing to do with an external source, just because the power dissipated inside, the temperature increases. And therefore, the increase in temperature can therefore affect the device electrical reliability and the electrical characteristics. And the power is given by where I square into R is the current and IV is the obviously the power dissipated. So, basically the self-heating effect which we get is because of the heat generated over a period of time, again cumulative in an action. There is a concept of thermal resistance which we will now put forward. So, if you plot drain current with respect to drain voltage, this is with self-heating and this is without self-heating. As you can see, with self-heating, the current is actually slightly larger. So, it is overestimating with overestimating as compared to with self-heating. And if you look at this equivalent model for the self-heating, then this is basically ID into VDS, which you see here, current flowing through the device. This is the current, which is basically, and this is the voltage which you see, there is the current source and the voltage, and it is a function of both IDS and VDS, and this is the thermal resistance which is parallel to the current source. Thermal resistance of the MOS device under consideration, and this is the thermal capacitance which you see here. So, typically it has been seen as the frequency goes on increasing, the difference between the actual temperature and the T0 as at frequency is equal to 0 goes on dropping down, right. Just look at this paper and this will help you to understand the phenomena of self-heating in a much more detailed manner. And we define thermal resistance as, if I give 1 watt of power, then what is the increase in temperature is defined as my thermal resistance, and that is given by this equation which you see here. So, if you do RTH here, this is delta T by P, and therefore, if I give 1 watt of power, how much increase in delta T is available to me is defined as my RTH. Fine. So, this gives you a brief idea about the phenomena of self-heating effect. So, let me recapitulate what we did for the whole lecture. We looked into basically the reliability issues of a device, because from henceforth onwards we will be moving into away from MOSFET into other regions where reliability is a major concern. So, we looked into basically the reliability. Within reliability, we looked into hot carrier injection or hot carrier effect. We looked into NBTI, right, and we looked into self-heating effects, right. We tried to give you an idea how this is basically degrading the device phenomena or the device electrical output characteristics. With this, let me finish this lecture. Thank you very much.